quote you. So that's why you were
Okay.
called.
You have to quote me. Okay.
Yes, yes, sir. There will be a slide on Einstein equation, right? So you will be there in that.
Okay.
I mean,
Wow.
I will I will refer to you.
Okay. I see.
So let's start, I think, because it's already 10:05
Yes, yes,
and
yes.
all the important people are here, except Paritosh, of course. So, uh, so part one was long back. Uh, in part one, we saw that there are some interesting mathematical structures called Lie algebras, which are
विश्वास record
very
करतोय ना?
important. क्या
मी
हुआ?
करताय. I'm
Okay.
recording.
हाँ, ठीक है. So, in part one, we saw that there are interesting mathematical structures called Lie algebras, and these are important, and we find them in physics very often. So, there were two mathematicians who did brilliant work, Elie Cartan and Wilhelm Kelly. They classified all possible finite dimensional simple Lie algebras, and they found four infinite families, which we call as the ABCD series. And if you look at them, these are just basically unitary groups, orthogonal groups, and symplectic groups, which we very often encounter in physics. Apart from these, there are exactly five exceptional Lie algebras. There are exactly uh, five of them, and all of them actually have found their place in physics. So, for example, G2 and E8, there are condensed matter systems where G2 and E8 have been theoretically shown, and the E series, E6, E7, E8, appear in specific theories of gravity, which we will discuss. So, before I go to this exceptional Lie algebras, we will start with a very modest approach, as you can see on the first slide, and I'll comment a little bit about why we are doing this, what this program of research is all about, because that's important. Some people think that it's just fancy mathematics, but uh, just to clarify that point, so we all know that standard model of particle physics basically explains three of the four fundamental forces, that is strong, weak, and electromagnetic force. And we have basically probed to the scale of about 10 raised to minus 18 meters, which is three orders of magnitude smaller than the this nuclear scales. The question is to answer what happens at scales smaller than 10 to the power minus 18 meters. Are there more degrees of freedom that will arise? That is the particle nature really true, or there is something beneath that particle? And as you probe smaller and smaller distances, you naturally have to deal with higher and higher energies. And so, at some scale, gravity also becomes important. And therefore, we must understand quantum effects of gravity. And thus, we are led to quantize gravity naively. Although in the community, there are others like Penrose and some others who think that it is also quantum mechanics which is incomplete. So we probably also need to gravitize quantum mechanics rather than quantize gravity. So these are some overall big picture things. But the overall story is we have a theory of gravity, classical theory of gravity, which works well, which is given by Einstein. And we want to study if we naively quantize that, what happens. So we know the answer. It runs
What
into
do you mean by
infinities.
gravitizing quant? You
Yeah,
said
so
something
that thing
gravitizing.
that thing is also not completely clear to me. But what he means by that is basically quantum mechanics as a theory itself is incomplete. There is something fishy about it. So he thinks that in order to make it consistent, uh, what needs to be done is basically incorporate gravity to explain that uh, part of quantum mechanics which you are not able to. That's probably what he means, but it's not completely clear to me what he means by that. Okay. I think I'll refer a
Hello,
video.
can you repeat
Uh,
what you said firstly?
just a minute. I think there is some disturbance here.
Someone's mic is on, I think.
No. It's my mic. My mic is only on. There is a dog barking here. That's why. Let me do one thing. You is one is led to quantize gravity because we have a classical theory of gravity, and at some very small length scale, we know that gravity will also become important because to probe that length scale, you will have to have processes which are highly energetic. And once you have highly energetic processes, Einstein's equation tell you basically that geometry comes into the picture because space-time gets affected. And so gravity will naturally play some role there. And that's why we need to understand the quantum effects of gravity. That's one way of thinking about this, putting gravity and quantum mechanics together. The other is by Roger Penrose. I'm just quoting him. I don't understand that completely. He says that instead of quantizing gravity, we must gravitize quantum mechanics. It's like the opposite statement. He says that quantum mechanics is incomplete. So to address that, one needs to gravitize quantum mechanics. That's a different approach. There is a video of Roger Penrose where he says this. I think some months back it came. We can later see that video and probably discuss that. Okay. Are there any questions?
What is the math for this energy probing you are saying, going to smaller scale than 10 raised to minus 18? What actually we are doing mathematically?
No, this is by pure. I am talking from experimental side of view. We have a theory mathematically which we have tested to this energy scale or this length scale, 10 raised to minus 18. That's what I mean. And experimentally, what I mean is basically if I go to, in principle, more smaller scales, will I see some deviation from the existing mathematical framework? And if I see deviation, that means there is something new happening and we need to explain that. And probably the answer is quantum gravity to that. That's the whole big picture. But of course, to these scales that normally we live, it's not important. But for a fundamental understanding of universe, it's important. So that is the point.
Okay.
So basically, so quantum gravity is the goal, of course. It's a very big word, but we will have a very modest approach here. And one of the modest approaches is basically supersymmetry. So it's basically a symmetry which relates fermions and bosons. You know that bosons and fermions have completely different statistics. Fermions follow Pauli's exclusion principle, while bosons do not. So they fall, and their spins are also different. One bosons are integer spins and fermions are half integer spins. But you can, in principle, put them into one Lagrangian where the fermions and bosons are related to each other by a symmetry, which is called as supersymmetry. And we will see how supersymmetry is nice because when you quantize such a theory, it has nice properties. So one can, in fact, consider a theory of gravity with supersymmetry, and that has exceptional symmetry E7 that I'll come to. That's the end slide of this talk, and I will not talk about all this very high level stuff in this talk. So we will have a very modest approach. So as you can see from the first slide, QFT. So let's start with what is QFT. QFT is basically putting together quantum mechanics and special relativity. So we all know that a relativistic particle satisfies this equation, nice equation. E square equals P square C square plus M square C to the power 4, where E is the energy of the particle, P is the momentum. If you go to the units where C equal to 1, we would like to put as many things as possible to be equal to 1. So we'll put C equal to 1. So E square is equal to P square plus M square. That's what you get. Now let's say I want to do quantum mechanics, one particle quantum mechanics with this. So I have a relativistic particle and I want to quantize that. So as we know from our non-relativistic understanding that the energy operator on the wave function is just I del psi by del t, right? So E square is minus del square by del t square psi. And if you write just the analogous Schrodinger equation for a relativistic particle, you will get this equation. That is del square psi by del t square is minus p square plus m square times psi. So given the momentum of the particle, it's like an eigenvalue equation that you have to solve. But notice one thing, that this is exactly like a harmonic oscillator, classical harmonic oscillator. This is like f equals minus kx. This is like f equal to minus kx, where k is this. Why? Because f is what? F is d square x by dt square. Okay. So we'll discuss this on the next slide. So quantum equation for a relativistic particle is like a classical force law for a non-relativistic harmonic oscillator. This is what we have. This is a very heavy statement, but let's analyze it piece by piece. What is happening here? So if you have a relativistic particle, okay, and if I interpret this, what is the question?
Yeah, how can this be a harmonic oscillator equation? Because in quantum mechanics, that E is an operator.
So
So
here
you are
also I have replaced it by operator equation, right?
no. Here, when you take that this p square plus m square is like an omega, that p has to be an operator in this case. If you write the Schrodinger equation in this
Yes,
manner.
yes. That's true. That's true. But I am trying to make a
that
different point here.
omega has to
Yeah,
be
yeah,
some kind
yeah.
of operator, not a value
Yes, yes,
like
yes.
harmonic oscillator.
Yeah. I understand that. But I am trying to make a different point here. The point is, this is like taking. So I'll write here. I hope it's visible. It's like h square psi equal to e square psi kind of equation. I'm just trying to write such an equation. I don't
Okay.
care what this is. Like this e square can be del square plus something. Doesn't matter. But
Okay.
I'm trying to write some kind of equation like this, where this h is just del by del t square. Okay.
Okay.
So this is just an eigenvalue equation in that sense. Okay. But for a relativistic system. Now what I'm doing is I'm drawing comparison between this equation and the normal classical non-relativistic harmonic oscillator that you get. Okay. It is same as that. You can just see that, right? D square x by dt square is minus kx. K is like p square plus m square here. Okay. So you can see that a classical classical relativistic particle, if you naively interpret this psi as the wave function of that particle, then it leads to some kind of a non-relativistic harmonic oscillator equation. So actually what I'm doing is not allowed, because in special relativity, you know that mass and energy are just two sides of the same coin. So you can in principle have processes where there are multiple particles involved instead of just one. So it doesn't make sense to actually write a single particle wave equation. There are many ways to show inconsistencies, which I'll not do it here. But naturally, one is led to consider systems with multiple particles in special relativity, just because mass and energy are convertible. And there are other arguments also, very good arguments to say why you need to consider a system with basically have a framework in which you can deal with multiple particles at the same time. Okay, so actually what is happening here is that the psi is not the wave function of the particle, but what you can think of it is like a field for the particle. So just like a photon has an electromagnetic field, this is the field of the particle. This is a classical field. This is a completely classical field. And so just like in quantum mechanics, we quantize the dynamical variables, which are the position and momentum of that particle. Here we will quantize this field, this classical field psi. And so you can see that this classical field sort of satisfies a harmonic oscillatory equation. So you can actually quantize this field. And for each momentum, you have one harmonic oscillator. That is, if you vary this P, you will have another harmonic oscillator, right? So you have a set of harmonic oscillators. These are called as modes. Okay. So each momentum is a mode. And what is a field? Field is basically a collection of all these modes. And there are infinitely many modes. Okay. So each mode is like a harmonic oscillator. Okay. So basically a quantum field, if you see, it is actually an infinite collection of these modes, oscillator modes. Okay. And you know from quantum mechanics, basically, that each oscillator has a ground state energy half h bar omega, right? So if you add the energy of all of these modes corresponding to each momentum, you have a half h bar omega. If you just add them, it turns out to be infinite. So the vacuum in a quantum field theory is itself tricky. It involves infinities. But the way we deal with this infinity is basically that we measure differences always. So we throw away these infinities. Okay. So this is a very, I will say, simplified version of what quantum field theory is. Basically, I am just showing you step 1 or step 0 where infinities start coming into the picture in quantum field theory. So
Nipun,
have this.
I think to cancel out this, we usually do that normal ordering stuff. Yes.
Yes. But what that actually means is you are trying to measure something relative to the vacuum, which is itself infinite. So it's like you have an infinite constant, and when you do some excitation, it's that infinite constant plus something, some finite quantity, and you measure the differences, so it doesn't matter.
Okay.
Right.
Okay.
But this infinity is actually there. If you do the calculation, you know there is this commutator of a dagger, which is a delta of 0, which is infinite. It is there
Delta of
actually.
0.
Yeah, mathematically. I mean, you can give a prescription like normal ordering, as you said, but in the most realistic sense, it is there. That infinity is there.
Okay.
So
Okay.
vacuum actually has some structure, and that structure is basically particle antiparticle keep on popping out, right, continuously in the space, right? So vacuum is really not just empty in quantum field theory. It's
Yeah.
particle antiparticle pairs continuously popping in and out, and in this way, it has some kind of infinite energy configuration.
Hello.
Hello.
I would like to add and also ask something. Like in non-relativistic physics, if you take a solid and there are plus ions on each lattice side in a discrete system, and each lattice point is like an oscillator. So but they are coupled oscillators. Like one oscillator is connected to different oscillators, and the collective effect is what we get as phonons, right? So
Yes.
the ground state of this, where there is no phonon, let's say at zero temperature, there is no phonon. This is very physically, there is no problem in this. And these are discrete systems. Now, if we take a continuous version of this, for every on real line in every point there is an oscillator, then this is what you are doing precisely, right? For every point there is a scalar field, and then you are quantizing it same as phonon. But phonons are like there are no infinities in this, in phonons in lattice systems. Is it because we are taking a continuous thing,
Yes,
and the
exactly.
infinities is coming from
In our case, we have a continuum firstly, and so what do you mean by summing over here? This sum is actually integral here. This is like an integral actually, and it's integral over three momenta, and all of the momenta run from minus infinity to infinity. So it's an infinite integral, right?
yes.
So that's why here you have this uh, big infinity that you get when you sum over ground state energies of all oscillators that you have.
So
Okay.
if we take like if we try to do this in a computer, so a computer we will take only large numbers or like lattices which are very close to each other. So they will mimic this thing, but because we are doing this mathematically, and so there are infinity, right?
No, I don't actually understand. Here, even if you do it on a computer, also you will restrict it to some kind of. If you try to basically discretize the space, uh, that will be different than what I'm trying to convey here, because actually discrete and continuum versions are different in many sense. Uh, it's not always that there is a nice continuous limit to go from one to the other. Okay.
Okay.
So, but my entire point is, if you try to put quantum mechanics and special relativity together, you have to deal with multi-particle processes in general, and this is just a free quantum field right now. Each mode, if you see, each mode is an independent oscillator here. There is no coupling between different modes. Okay, each mode is a different oscillator here, so it's like a free quantum field here. And each mode, because it's a harmonic oscillator, it has a ground state, and that ground state is half h bar omega, where omega is this. I forgot to mention. Omega is root of p square plus m square.
It's
Okay.
like one phonon is not interacting with another phonon.
Yes, exactly. That's why we call it a free quantum field. Now you can add interactions to it. Okay. And you can compute processes, scattering processes, or other things. Okay. So this is a very oversimplified picture, but we will go with this only because it's more intuitive and conveys the point. Okay. So there is nothing to discuss here, but I hope these points are clear. So what we have done is basically we have taken quantum mechanics and special relativity, and we have put them together, and we see that the first place itself we start getting infinities, and infinities are not nice because of course you never measure infinities in real experiments. If you want to compute some observable, you need to have some finite results, and as Debo pointed out, one way is to give some prescription to deal with these infinities. But the other prescription, a very nice one, is to include another degree of freedom, which is a fermion in this case, which has an energy minus half h bar omega for each mode. Okay, so for each bosonic mode, you have a fermionic oscillator, or for each bosonic oscillator, you have a fermionic oscillator with exactly the negative of that energy. And then the energy of the vacuum is zero. And that's what happens for a supersymmetric theory. When such a thing happens, we say that the theory is supersymmetric. So a theory with fermions and bosons, which are related by a symmetry, which is supersymmetry, has a zero vacuum energy. Okay. So which is nice. Divergences are cured not by some prescription, but uh, but actually by a calculation, real calculation. Okay. So this is nice. So this is the first hint that divergences can be removed by more symmetry. And this is the approach that we are going to take. We are going to add more and more symmetry to improve or remove these divergences that can appear out of a calculation in a quantum field theory. Because ultimately we don't want to run into infinities, because this means the theory runs into unpredictable sort of regime, which is not good. Okay. So for some reasons, let's jump into this sort of an expression. This is an integral, and you can guess this is also called as the partition function. And in Feynman's way, this is nothing but the probability amplitude. Uh, so what is this integral? I'll explain physically what this integral is. Uh, this think of this as a Lagrangian, okay? Lagrangian of some system. And what this integral is basically doing is it is summing over all kinds of paths. So usually classical equation of motion is derived by extremizing the action, right? So it's a stationary point of the action. But in quantum mechanics, the particle need not follow the classical equation of motion. It can go through all possible paths. So this is what roughly this integral is doing. This is a discrete integral right now. This is like an n vector, okay? And this xt means x transpose, and A is a positive symmetric matrix, which means its eigenvalues are all positive for this integral to be convergent, of course. So this is the integral roughly that you get when you try to do quantum mechanics using Feynman's way. So this is called as a path integral, but right now this is not actually a path integral. This is just a discrete integral over a vector. Okay. So one needs to solve this. This is physically related to probability amplitude. So these kind of integrals is what we'll run into. Okay. So there is a very nice way to solve this, right? So since A is a symmetric matrix, we know that we can actually perform a rotation and go to a coordinate where x is diagonal. So that is what I have done here, right? I can always diagonalize a symmetric matrix by a rotation. And since it's a rotation, there is no Jacobian. So dx is same as dy, right? Because rotation preserves norm. So there is no Jacobian. So from step 1 to step 2, what I've done is basically I have performed a rotation such that A becomes diagonal. And now it's just a product of integrals. It's just a product of Gaussian integrals, which you can solve. And what you'll get is 1 over determinant of A. Determinant of A is basically product of the eigenvalues. Okay. Is there a doubt or a question here? We can do this in proper steps also. So if you want, we'll do that. So this is clear, right? Hello?
I think it's clear.
Okay.
Yes.
So this is what I'll call as the bosonic path integral. The basic object is x here. Okay. And you can think of it as summing over all kind of paths for the particle. And this A, what you can, so you can ask the question, what is this A? So A, I will say that this A contains the dynamical information about the system and it is related to the Lagrangian. For example, a very simple example is you can take A to be derivative operator or del by del t square. Okay. It can be a derivative operator also because it's also a linear operator, right? So it can be del by del t square also. Then it's like x dot square roughly.
Nipun, one
It's like-
point. One
Yes.
technical point I have to mention. You defined that combination x transpose A x to be L, but in general in path integral, that is the action. Normally,
Yes, that's
I mean-
true. But the reason I don't have a action here is because there is no time to integrate over. You see, this is like a zero-dimensional system.
that's true. Okay. Yeah.
Yeah.
I mean,
So you can have a zero-dimensional system also. So in zero dimensions, you will have this path integral. This is like
okay.
this is like a single point on which you have this x degree of freedom.
This
Okay.
is like a generalized Gaussian integral. What you have written.
Yes, exactly. But I'll also interpret it as a dynamics in zero dimensions.
Yeah, true.
Yeah. So,
What do you mean by
that's
zero
why
dimension? I did not understand zero dimension.
see, usually what is the action? Action is dtl. Okay, right?
Yes.
Now insert a delta function here of time. You will get some Lagrangian evaluated at some specific point, some time slice.
Right.
So this is what this action is. There is no time here in this action.
Okay.
It's like
Mm.
you have a single point. You don't even have space here. This x is actually not space in that sense. It's just a variable at a point. You are assigning a vector this at a single point in space, single point, and you are just kind of defining a path integral for this vector or this. So it's like this x1 x2 xn defines a state at that point p. You can have different states. This can be, for example, x1 prime xn prime. Okay, and you can define sort of probability between what is the probability that if I measure at p I have this state or I have this state, and it will be related to some kind of a path integral like this. Okay, so this is related to probability amplitude because it's a distribution. It's a Gaussian distribution, right?
Mm.
So this is exactly like statistical mechanics. Okay, that's why I said zero dimension. Okay, so yeah, so I was making a point here. In general, what happens is basically this x itself is a function of time, as Debojyoti pointed out. In normal classical mechanics, this x is the position, and that position is a function of time. So this x is itself a function, and therefore there is an integral over here, there is dt over here, and this is called as the action. So there is actually an action in the exponent, and this a is some kind of a differential operator. It's like del by del t square, for example. So you get x dot square. What is x dot square? It's just the Lagrangian for a free particle, right? And then you can have, of course, interaction terms and all those things. But in general, that's why to just remove all the subtleties, I have just focused on the very simple system where there is no time and there is just a Gaussian, generalized Gaussian integral. Okay, but this is what it is. I mean, even in the complicated cases where you do quantum mechanics with harmonic oscillator, you define path integrals. X is a function of time there. This A will be a complicated operator there, and you have to solve for the eigenvalues of that differential equation then. Instead of a matrix, that will be a differential equation. Okay, that you would have to solve to get the eigenvalues. But the answer is this only. It's 1 over square root of determinant of it. Okay, so roughly this is what I'll call as the bosonic path integral or bosonic dynamics. Let's say the reason is because it involves variables that we know. Okay, this is a very bad reason, but let's go with this. Okay, we have already discussed, so let's skip this slide. Okay, so normally the variables that you normally use, they commute. If you take x times y, you get y times x. This is what we understand. What we don't understand is if something anti-commutes. So there can be variables where instead of commuting, the anti-commute. Theta times theta is minus eta times theta. And therefore we use Greek alphabets, which we don't understand. So these kind of variables are useful to describe fermionic degrees of freedom. Okay. And the reason is very simple. The square of such a variable is always zero. Why? You can just put eta equal to theta here, and you will find that theta square is minus theta square, which means theta square has to be zero. Okay. And if you think of theta as some kind of a creation operator, think of theta as some kind of a creation operator. Usually in quantum mechanics, you have a dagger acting on the ground state. It gives you the first excited state and so on, right? Similarly, you have a sort of a oscillator where it satisfies A dagger is 1. This is anti-commutator. So normal harmonic oscillator is A dagger is 1. So this is bosonic. This is the fermionic oscillator. Okay. In this case, you will find that A dagger square acting on 0 is 0. So what it means is that you cannot have two particles in the same quantum state. A very nice way to put the Pauli's exclusion principle. So the statistics naturally comes out of this. That's why fermions, we deal with fermions with these kind of anti-commuting variables, which are called as the Grassmann variables. So is this point clear? So that we can now move to dynamics of fermions.
I wanted to ask, how are you adding a fermion mode to boson mode? Usually we treat
These are
them
just
separately.
these are just numbers right now. I mean, just think of it as numbers. There is no uh, these are not fields or anything right now. These are just numbers, normal numbers like how you think of 2, 3, 5. Think of these as some kind of abstract numbers, theta and eta. Okay. But what was your question? I mean, operation?
Earlier, you said earlier there was slide, right, that we will add a fermion mode to boson mode to
Add.
remove.
Correct. So by adding, I mean I'll add some term here and some integral here. Okay. So by adding, I will clarify this. What I mean by addition exactly. Okay. I get your point. See, you want to ask, you cannot add an anti-commuting number to a commuting number. I think that's what you are saying.
Yes.
But that's not what we will do, because you see, if I have two anti-commuting numbers, they are commuting. Take eta times theta. This is a perfectly fine normal real number. Okay. You can show that product of two different anti-commuting numbers is a commuting number.
So it's more general than commuting. I mean,
So let's do a simple example. Eta 1, eta 2, these are two Grassmann variables, which means consider another pair of Grassmann variables, eta 3, eta 4. These also satisfy this, right? Now consider product of eta 1, eta 2, eta 3, eta 4, right?
yes.
Now, do these together commute or anti-commute? That's the question. You can easily see I have to pass N3 twice, so it won't pick up a sign. I have to pass N4 twice, so it won't pick up a sign. So this is same as N3, N4 times N1, N2. So these are actually normal numbers, C numbers.
They both commute.
Exactly. So you can always form normal numbers out of anti-commuting numbers, but you can never form anti-commuting numbers out of normal numbers. So these are called C numbers and these are called A numbers. Anti-commuting numbers, and these are C numbers, commuting numbers. Okay. So nice. So we have two kinds of objects. One are commuting numbers, which I'll use to describe bosons, and the other are anti-commuting numbers, which I'll use to describe fermions. Because naturally, the statistics comes out of such kind of algebra, as I showed you here. Okay. So now let's do dynamics with these variables, right? Let's sum over all kinds of paths. These variables, by the way, are called Grassmann variables. So let's consider a path integral again, or a partition function with such kind of variable, where theta is now an anti-commuting number or variable. Okay. Now, naturally here, you will have B to be anti-symmetric matrix because theta and anti-commutes with itself. Okay, you can show that it has to be an anti-symmetric matrix. If it is a symmetric matrix, the answer is just 0. That you can show. So in the case of boson, that matrix was anti-symmetric. In the case of fermions, this matrix is antisymmetric. Okay. Now, what you can show is basically if you evaluate this whole thing, remember that the square of a Grassmann number is 0. So we can actually solve this exactly. And it's very easy to do. And I'll show you how. Let's consider the case of two Grassmann variables. Okay. So d theta 1, d theta 2. Okay. And you have exponential of minus theta 1 b12 theta 2 plus theta 2 b21 theta 1. But because b21 is minus of b12 and theta 2 and theta 1 anti-commute, right? So I made some sign mistake here. This minus sign is overall. You have b21 theta 1. Okay. Okay. So because this b21 is minus of b12 because it's an antisymmetric matrix and theta 2 and theta 1 anti-commute. So again you will get this thing. Okay. So you'll get d theta 1 d theta 2 exponential of minus 2 times theta 1 b12 theta 2. Okay. Now you can expand this exponential. What is the thing? You can do very nice things with this. 1 minus 2 times theta 1 b12 theta 2. There are no higher order terms. Why? Because when you square this, theta 1 square is 0, theta 2 square is 0. So there are no higher order terms. So exponential is actually a linear function in Grassmann variables, which is a very nice thing. So you can solve integrals exactly. And here comes the trick. The next thing is to define these integrals. So Bayesian defined this. This is called as Bayesian integration. So d theta 1 is 0. D theta 1 is 1. This is the definition, basic definition. So the first term is 0. Okay. And the next term, as you can see, you will get just 2 times b12. And this is nothing but 2 times square root of determinant of b. Because what is b? B is 0, b12 minus b12, 0. So determinant of b is actually b12 square, right? So this is what we have here. So I hope this is clear. If there are any questions, you can ask me. This is very simple. I mean, with these rules, these are the rules here. This is called Bayesian integration. Because the square of a Grassmann variable is 0, the exponential function is just a polynomial, simple polynomial. And then using the rules, you can integrate it. And you can actually show that if you
in terms of these rules, there cannot be any polynomial of higher order. I mean, all are linear. Any functions will
yes,
be
you
linear.
can add more variables. So you can have complex variables, for example.
I
You
can
can have
conjugate them, but in a single variable, there cannot be higher of power than one.
Yes, definitely.
Mm.
So you can have theta 1, theta 2, theta 3. Then you can have a x square kind of term where there are cross kind of. So there can be somewhere here some kind of a term like theta 2, theta 3. Then you can have a cross product term also in the exponent. So that is allowed. If you have n variables,
Okay.
at most you can go till x to the power n, right?
Okay.
Because from each you can choose one theta.
Mm.
So but the statement that you said is true. Any exponential function of a Grassmann variable is always a polynomial function.
Mm.
So as it turns out, although their algebra is not intuitive, but maths with Grassmann variables is very nice. It is very easy, in fact, easier than normal bosonic integrals that we do.
So we should have a high school level Grassman algebra rather
So,
than
so I
usual.
had I had this discussion. We had this discussion with my RAC advisor, Professor Gangal.
Okay,
So,
okay.
so he said that these variables are not intuitive because these are not taught in high school. But if these are also taught, then this is the starting point. You can start teaching quantum mechanics in
Start
first year.
with the Grassman variable, then we go to the real variables.
Yeah, see, they're
Right.
so easy, very easy to do.
Yes,
You can
I mean
exactly
we
uh,
can define their calculus in class 6 standard or 5 7 standard.
exactly. I mean, exponential function one has to first define,
Yeah.
at least.
This
Polynomials,
anti
I think everybody studies in till seventh, eighth, or ninth.
I wanted to ask, historically, did the anti-commutator came later? Was it inspired from this or something?
So I currently do not recall the exact order of the events, how it was, but the problem, the way this actually came about was Dirac gave his Dirac equation. If you know this, he was looking for a first order relativistic quantum mechanical equation, and he ran into a set of equation which we now call as the Dirac equation. But the trick was that that wave function or the field is no longer just a single field, but it's actually a it's a column vector actually. So the same problem persists in that equation also. It's a coupled set of, so you see, this, right? You can have a higher order differential equation, but you can always decompose a higher order differential equation into a set of lower order coupled differential equations. Simple example is Lagrangian and Hamiltonian formalism. Lagrangian, you have a second order differential equation. In Hamilton formulation, you basically split it into two first order differential equations. So roughly this is what happened. So Klein-Gordon equation, which was basically what I showed you in the first slide, p square, e square equal to p square plus m square. That is the basically relativistic equation. Dirac did this, and then they realized that one has to do basically uh, quantum field theory, not one particle quantum mechanics. And there they found out that basically one needs to, so so as I said earlier, you want to quantize the dynamical variables. In case of fields, the dynamical variables are the field and the field momentum. So when you want to quantize that field, the fermion field, they found out that they have to use anti-commutator for the right statistics. Okay, so the statistics, this Pauli's exclusion principle or the earlier known fermion statistics was the main motivation to consider this.
Nice.
Okay. So as you can see, this is nice. So one can consider a product of these two partition functions, the bosonic and the fermionic, and you will get just one, in fact. You can cancel them exactly if this determinant of B is same as determinant of A, right? And this is what happens in a supersymmetric theory. In supersymmetric theory, this B is related to A. That's what we mean by symmetry, right? Symmetry relates to objects. So in this case, it relates this matrix B and the matrix A, and it says that the determinant of the two matrices must be same. It will give you exactly one. The reason,
What
so this one is not, huh,
B and A? What is the relation between B and A actually in supersymmetric theory?
So in supersymmetric theory, so usually you know that in Dirac equation you'll have some gamma mu del mu here, some psi bar gamma mu del mu psi. It will be something like this, right? Lagrangian. So what it does is basically it tells you this del mu. So you know that this gamma mu del mu square is just box, right?
Hmm. Hmm.
So if you compute, for example, phi bar box phi or del mu phi ka path integral, you will get determinant of box.
Okay. Okay.
And from the Dirac side also, you will get some kind of determinant of box, except there will be some extra factors there that you have to take care of. That
Okay.
that factors will actually tell you whether this exactly cancels, this determinants exactly cancel or not.
Okay.
And those are somewhat related to, those extra factors that you'll have of half or all those things, those are like the analog of B, basically.
Oh, okay. Okay.
So in this is a very simplified system. See, but this simplified system is also teaching so many things to us, right? In very simple language. If you want to just have a path integral which doesn't depend on any eigenvalues, it's just a constant number, or the partition function is a constant number, then what does it tell you? It tells you the determinant of B should be equal to determinant of A. That's what it is. And that's what you will find even for a basic West-Zumino type model, which has just a scalar and a fermion, a Dirac fermion. Okay. So this is nice. So simple integrals have taught us nice things, right? One of the things is you can design or fabricate integrals in such a way that their product cancels and you are left with just a number. And this cancellation of determinants is actually related to, in technical terms, cancellation of vacuum energies of the bosonic and fermionic uh, degrees of freedom. And this was first shown by Bruno Zumino, who is one of the founders of supersymmetry in 1974, and from where the journey of supersymmetry sort of began. Okay, so we have actually done this in a very simplified way. If you actually read that Bruno Zumino's paper, it's complicated because it involves more realistic things like uh, scalar fields and all those things. We have just done simple normal integrals of bosonic and fermionic variables here and shown cancellation of determinants. Okay. So this is nice. So now we are almost towards the end, about 5 minutes. So this is where I want to quote Debojyoti, because he can explain, if someone has a doubt, he can explain how to go from this action, this which is called as the Einstein-Hilbert action, to this equation, which is the Einstein equation. And also, if someone wants to know what kind of solutions this Einstein equation admits, I think Debojyoti is the right person to talk to. So that's why I wanted to quote him. And for flat space, you will find that you can simply take the trace of this equation. So these are called as the Einstein equations. And right now, there is no matter here that I have added. Usually, there is a matter on the right hand side instead of 0. And the usual interpretation is basically that matter curves space, and space tells, or geometry tells, how matter moves. So that's the basic interpretation of Einstein equation that's usually told. But in the case when you have no matter, you have just the gravity to begin with. You have a very simple equation, and you'll find that this R mu nu, which is called as the Riemann tensor, that's 0. So this theory, this is the action of the theory. This theory has 2 degrees of freedom, or 2 propagating modes, you can say. Just like an electromagnetic wave in free space has 2 degrees of freedom, right? Which are orthogonal to the direction of propagation. So the plane perpendicular to the propagation of the wave, that contains the sort of polarizations, the physical polarizations. Similar to that, gravity also has gravitational waves, as we have detected. And these gravitational waves also travel at the speed of light. And their degrees of freedom are also constrained on the plane perpendicular to the direction of propagation. Okay. And we assign to these degrees of freedom something called as helicity, which is basically the projection of spin onto the momentum. And photon, for example, has helicity +1 or -1, depending on which way the polarization is. And graviton, so photon is a spin 1 particle. Graviton is a spin 2 particle. So it has helicity +2. This you can do. So usually what one does is basically solve Einstein equation and sort of get interesting solutions, such as black hole solutions or other things, which people try to study in general relativity. But this is not the approach that I am taking. I am going to take perturbative approach, which means just like you can scatter photons in the theory, uh, you can scatter two photons through electron basically. Uh, what I'll study is basically graviton scattering. So graviton is basically a particle corresponding to the gravitational waves. So what photon is to the electromagnetic wave, graviton is to the gravitational wave. So you can think of them as actual particles, and you can scatter gravitons here. Okay. And then study basically processes where quantum mechanics is sort of kicks in. Okay. And here is the most important slide. If you scatter gravitons in this theory, so by scatter I mean here mathematical scattering, not the experimental scattering. We have not detected gravitons yet, but we have detected gravitational waves. So if you do a quantum calculation of this, you will find that you will run into infinities, in fact, and this cannot be cured by. This cannot be cured. I mean, you cannot get rid of these unless you add something more. And of course, as we saw, what you can do is you can add fermions and consider a supersymmetric theory where the hope is that you can cancel these divergences and get some nice finite answers, right? So this is what it is. It leads to a unique theory of gravity, so which is called as the n equals 8 supergravity theory in 4 dimensions. So as you can see, it's a very complicated theory, and that's why I have no slide for this here. It has 128 bosons and 128 fermions, so it has total of 256 degrees of freedom. Okay, it's a very complicated theory in 4 dimensions, and it has been shown that this theory has a nice symmetry, which is the E7 symmetry, one of the exceptional Lie algebras that we discussed last time. And what this symmetry basically does is it mixes different degrees of freedom. So it rotates these 128 bosons amongst each other in some way. Okay. In fact, it rotates all of them. All of these 256 degrees of freedom amongst each other. So you already have supersymmetry, which relates bosons to fermions, but on top of that, you also have this E7 symmetry, which basically mixes bosons and fermions, all of those particles together, those 256 particles. Okay. And till date, no calculation has shown any divergence. But absence of divergence does not imply that it is a proof of convergence, because you have to do a calculation at more and more loop orders to really find if there is a divergence in the theory. So this is an open sort of question, and which people are trying to answer. And I am also trying to see this, understand this kind of problems. And finally, to the question of whether supersymmetry is real or not, of course, till date, it has not been discovered. But again, the approach is absence of proof is not the proof of absence. So we haven't found supersymmetry yet, but that doesn't mean it's not there. So we will take that approach for now. And finally, I'll end with this slide, which is to list some Nobel Prizes in physics related to the fundamental forces. So 1979, for example, Sheldon Glashow, Abdus Salam, and Steven Weinberg, they got for this electroweak theory. And in 2004, Politzer, Cross, and Wilczek got for this asymptotic freedom of QCD. And we don't know when we will have something like this for quantum gravity. It's still a very big problem to be solved. And thank you. So you can ask any question if you have.
Like if the divergences are answered, what is left to solve?
Divergences are cancelled. So all the problematic part is cancelled, but you still have some finite answer, right? You have some number with you. You can that number you can in principle you should be able to match with some kind of experiment, right? I am done, so you can ask any question that you have.
Uh, I mean, like in how I was taught quantum field theory is you start with two different fermions bosons, right? You either take fermions or you either take bosons, at least in non-relativistic. So you don't mix them too. So
Mhm.
if this is possible in real systems, it might
No,
be
it is
possible.
possible, right? It is possible. Standard model of particle physics has both fermions and bosons. You can have a Lagrangian where both are there. Normal electrodynamics. Two electrons have experience electromagnetic force. The force is carried by photon. Photon is a boson. Electron is a fermion. So you can have a normal non-relativistic system also has this, right? This is not a property of some fancy mathematical theory. It's just normal physics.
The coupling is through a boson, right? Always.
Uh, so, uh, what actually you mean is the force is carried by
Hmm.
boson.
Right.
Ah, ah. Yes, yes, that's true. In the standard model, all the forces are carried by bosons, and the matter is made up of fermions.
Hmm. So.
But
Hmm.
you have a Lagrangian which has both fermions and bosons in it. So it does not require supersymmetry. Supersymmetry is an additional thing that you are giving on top of a normal Lagrangian. So you should not think that only a supersymmetric Lagrangian has both bosonic and fermionic. Normal electrodynamics theory, if you write in the field quantum field theory language, it has the Dirac field and the BH field, AMI, or the electromagnetic field, which is a bosonic field.
Hmm.
Depojo, you want to add something about general relativity or Einstein's equations?
I don't know about that gravity and graviton scattering. I think something I have read in Feynman's book. I think lectures on gravitation. So it's
Yes,
maybe
he has very nice
some.
points about why. So he firstly argues why spin two theory for gravity.
Yeah, yeah, true.
Hmm. So he starts with a very nice approach. He starts with spin zero. He eliminates spin zero because
Hmm.
if gravity was mediated by some kind of a spin zero field,
Bending of light,
then
bending of
you
light. Yeah,
light
observe.
exactly photon would not couple to
No,
a
you
scalar
cannot
in that
electromagnetic.
theory. And yeah, and experiment we have evidence that light is bent by, I mean, light
Hmm.
couples to gravity, right? So
Hmm.
that
True.
cannot be the case. So the next candidate is spin 2,
Hmm.
and
Because
that works.
and spin one, if you go to spin one, you need a gauge degrees of freedom, and they need to
Yes,
evidently
yes,
conform to electromagnetic field. Nothing else. I mean,
yes,
with
yes.
that
And
momentum.
uh, also there is one nice thing that you can show. All odd spin particles have this property that like charges repel
Hmm.
and opposite charges attract, while for even spins you can show that like charges attract and unlike charges repel.
Huh?
So for gravity, you see, you take masses have the same sign. So these are some like charges, they attract. But if you take two electrons, they repel.
Hmm. Hmm.
The force that is carried by electromagnetism is a spin one kind of field,
Huh.
but gravity
Okay.
is a spin two field. So it's odd versus even, something like this. And the
Okay.
simplest even that you can consider for gravity is spin two.
I see.
Yeah. So this all is also given in Feynman's book.
Okay. I
Since
haven't
we are talking about
but
no, you
Uh-huh.
continue. I'll ask later.
yeah, Aditi.
No,
I
I
think
just
both
want
stop.
this is completely different. So I think you hello.
बोल ना.
So what I wanted to ask is completely unrelated to what you were talking about. I was just wondering, like today also we had this very starting discussion about Chern-Simons. So why is it that Chern-Simons is only valid in odd dimensions, like 2+1 or 4+1
Uh,
or so on?
Very nice. So you can show that so take any kind of Chern-Simons theory. ठीक है. Epsilon वो टेंसर होता है ना, एप्सिलॉन म्यू न्यू रो सिग्मा जो भी है.
Yeah, yeah.
In even dimension you can show that it's a total derivative term. Basically it's just a topological term. Total derivative term means you can ignore in the action. But in odd dimensions one term always survives. We can actually do this here also. It's very simple to show. So here take for example this kind of uh, term ai del j ak. ठीक है. 3 dimension epsilon ijk is
Okay.
3 dimensional antisymmetric tensor Levis beta. ठीक है. Now if I partially integrate this is action d3x. Okay. If I partially integrate, I'll push this here, but I'll recover the same term again because I and j are antisymmetric, right?
Yeah.
So I'll just get minus del j ai ak, which is same as this term. So, hello.
बोल ऐकू येतंय.
Now let's do this in 4 dimensions. Epsilon I j k l ai del j ak and let's take al. One has to put the derivatives properly. Del j. So in even dimensions, what you can do is basically keep on doing this kind of partial integration. Okay. What you will get is something like this after partial. I'm not sure about this right now. I forgot whether there are two derivatives. There cannot be two derivatives because derivatives cannot be antisymmetric, right? If you do
Right.
partial integration at 0, so you can only have one
Yeah.
derivative. So you
One
have to add
derivative.
another field only. But here you can show that this is like a total derivative term, but I don't exactly recall how this is a total derivative term. You have to partially integrate and show that it's a total derivative term. So basically the point is you can do partial integration. You can throw this del j here or here, and it should be something like a should be minus a, something like this. Therefore a is 0.
That's right.
Something,
Okay.
something like this.
So due to the antisymmetric part from the Levi-Civita, you cannot have such kind of theories in even number of dimensions.
Yes.
Okay.